You guys have only have 2 more videos to go, and then all the chapters are up, and I can start focusing on the test. Whew, I've recorded so many videos today. I just chugged a bunch of caffeine, so I apologize for how hyper I am. Let's get through this video. Okay, sorry, I'll calm down now. So, chapter 11, we're going to be talking about the RMS error. RMS stands for root, mean, square. Mean is referring to average, root is referring to square root, square is referring to something squared, like 3 squared is 9. So let's start with errors, and then we'll get to this root, mean square part of it. With the regression line, so this line right here is my regression line, the line we can use to predict weight from the height for this specific data. We are given a few different points that we want to look here. So A, B, C, D, and E. A has a large positive error. What that means by error is how far it is away from what we would predict it to be. A is way far above it, so it's positive because it's above. B, same thing, it's above the predicted value. We would predict for 76 inches, we predict it to be down here at like 200. And it's clear up here at 430. So that's a large positive error. Then we've got C, that's a small negative error. E, that's a large, actually not large, sorry, it's just a positive error. And D, that's a negative error. So error is simply referring to how far away from the line of prediction it is. How far off is the actual data from what we predicted it to be. If it's above the line, it's positive. If it's below the line, it's negative. Okay, we've got this example again. We looked at this in the previous slides for chapter 10. This was the one with the really weak correlation. For men aged 18 to 24, the relationship between height and systolic blood pressure can be summarized as follows. Estimate the average blood pressure for men who were 6 feet tall. I'm still going? Yes, sorry. I hit a wrong button and I thought I paused the recording and then I thought I lost it, but I didn't. We're good. I've got to calm down a little bit, huh? Sorry, I'm very hyper. So 6 feet is 72 inches. We actually have already done this problem. We did it in the previous chapter using our 4 steps, and when we did it, we estimated it to be 122.14 millimeters. So we're just going to use that. Again, to get there, I used the 4-step method, where we find the z-squared for y multiplied by r, that becomes the z-squared for x. I said that backwards. Find the z-squared for x multiplied by r, find the z-squared for y, and then change that to standard deviations, change that to raw numbers, and add it to the average. Hopefully that makes sense. So this is what we predicted when we did that in chapter 10 notes. What we found for a 72-inch tall man, we found that this is not correct. For a 72-inch tall man, we found that he actually had a blood pressure of 135. So we predicted 122, he had a blood pressure of 135. So what I want to know is the RMS error for that. And to find that RMS error, so it's not just the error. I know it's a positive error of about 13. I want to find the RMS error. And there's a formula for that. You know what? I did not read that right. I'm sorry, I was looking at a previous problem. Let's try this again. The residual is what we want to do. So that's what I just said. It's about 13. That's the error. It's positive because it was higher than what we anticipated it be. Sorry, I jumped ahead a couple slides. Okay, so the residual is simply the error, and it is almost 13. Let's see, it's 135 minus 122.14. Let me try typing that again because I missed the 3. Almost as much as I miss you guys. Like, really, it's weird to be teaching to an empty classroom. Okay, that is the residual. That's how far off it is. The RMS error, so I threw that out there a couple times. The RMS error is how big are the errors on average. So if I take all of the residuals, so we look back at this slide, if I take every single dot here and find the residual, how far away it is from that green line, and average it, that would give me the RMS error. We don't have to do it dot by dot though. We have a formula for it. To find that RMS error, we use this formula. And you will know you need to use that formula if it says RMS error or if it says how far is the prediction off by. Or is the prediction expected to be off by? Okay, so I need to add this formula to our formula sheet, so I'll get that updated. Notice it's using 2 parts of the 5-number summary. We need R, that correlation coefficient, and we need the SD of Y. So this is the same question where we estimate for a 72-inch tall man, we got that 122.14. Now I want to know how much we would expect it to be off by. So the RMS error or the expected residual. How far off do we expect this prediction to be from what we actually expect, from what the data will actually show? So to do that, we have this formula, the square root of 1 minus r squared times the SD of y. And if we look up above, we have r is negative 0.2. Squared times the SD of y is 14. Okay, I'm going to type that into my calculator. Pay attention to how I type it in. Negative numbers squared are positive. So a lot of you, your first thought was, oh, let's change this into a plus. You cannot do that because you have to square it first. And when you square it, what happens is this becomes 0.04 and it becomes positive because a negative number squared is positive. So it's going to do this. I'm just going to type it all into my calculator in one step so that I don't mess it up with my with any order of operation errors that I might make. So I'm going to do the square root of 1 minus negative 0.2 squared. And then outside the square root there, so I'm going to arrow, so I'm outside of it, I'm going to multiply it by 14. And I would expect this to be off by 13.7. Which, if you remember from our previous one, it was off by just about 13, so that's pretty accurate there. Okay, we're going to treat the RMS error similar to the standard deviation. So the standard deviation is like how far away from the average most people are. The RMS error is how far away from the regression line we would expect people to be. So in other words, how far away from the average, because the regression line is the average, how far away from the average is that dot going to be? That's exactly what the standard deviation is. It just has two different names because they're dealing with two different things. Regression is dealing with both an x and a y variable, versus a standard deviation is just dealing with a single variable. So the RMS error actually is the same as standard deviation as far as percents go. So if you remember our empirical rule, where one standard deviation away was 68%, two standard deviations away was 95%, three standard deviations away was 99.7%. Same thing applies for regression lines and RMS errors. We would expect 68% of the dots to be within one RMS error of the line. So within this range, 68% of our dots will be there. And then within two RMS errors, so within this range, 95% of our dots will be there. Okay, estimate the final score for someone who got an 81 on the midterm. So we know that the final scores are what we're estimating. 81 is what they got on the midterm, so that's our X. And I think we've already done this problem, but I'm just going to go through the 4 steps again, just as a reminder for how to do it. So we're going to take our average, or our z-score by doing 81 minus the average for X over the standard deviation for X. That is 16 over 16, which is just 1. Multiply that by 0.7, the correlation coefficient. It becomes 0.7. So somebody who is 1 standard deviation above the average on the midterm is going to be about 0.7 standard deviations above the average for the final. That's our prediction. Keep in mind, this is a prediction, so it's not exact. Just because you get above on the midterm doesn't guarantee you're going to get above on the final. This is just generally speaking, this is probably what will happen. We're going to take 0.7 standard deviations above the average for the final. So 0.7 times that standard deviation of 10 for the final is 7 points. Well, 7 points above the average is 67. Okay, 67 is what we would predict for the score. And then approximately 68% of the students who got an 81 on the midterm would be between blank and blank. This is saying do one RMS error either direction from the average. So we know RMS error is 1 minus r squared times SD1. 1 minus 0.7 square root of that times SD of y. Type that into my calculator. Square root of 1 minus 0.7 squared times 10 gives us a standard deviation of 7. Okay, as you're watching these videos, remember you can speed it up or slow it down. So if I'm going too fast for you, slow it down to 0.75 times. Or just pause it for a minute to get caught up with me. If I'm going too slow, speed it up to 1.25 or 1.5, whatever is best for you. I just said that and then I forgot what the answer was. 7.1. Okay, what that means is we would expect 67, give or take 7.1, is where 68% of our students should fall. So if we do 67 plus 7.1, that is 74.1. 67 minus 7.1 is 59.9. Okay. Then we want RMS error, 2 RMS errors, because it's 95%. So let's just do 67 plus or minus 2 times 7.1. And I do need to pull my calculator up for that one. 52.8 to 81.2. What that's saying is if I were to draw a scatter plot of all the scores, draw the regression line, 95% of the data for students would fall between 52.8, wherever that is on the y-axis, and 81.2, wherever that is on the y-axis. This line should be in the middle of that, so we'll pretend it is. Yeah, that just says exactly what I just said there. Shows you some of the points are outside on this one, but since it's 95%, this contains almost all the points. If the scatter diagram is football shaped, the RMS error can be used like the standard deviation, but as we talked about, RMS error is for a regression line, so it's dealing with two variables, both an x and a y, or the explanatory and the predicted, versus a standard deviation just deals with one variable. So we've got the same thing that we have for the empirical rule applies for RMS error, just like it applies for standard deviation. Would you be surprised to find out that someone who got an 81 on the midterm got a 60 on the final? Well, let's go back and look at what we said here. Two RMS errors is everything from 52.8 to 81.2. Two RMS errors away from the average is 52.8 to 81.2. Somebody who got a 60 on final? Nope, not predicted, or not surprised. Then two RMS errors of the average. Of the predicted score is what I should say. And that predicted score is simply the average or close to the average of all those people who did take the final, who got an 81 term. Okay, a 90 or a 40, I would be surprised on those because those are outside 2 RMS errors away. You can find 3 RMS errors away because that should contain 99.7% of the data. So if you want to, you can just find 2 or 3 and say it will fall within 3 RMS errors, I believe. Let's check. It was 7.1. Yeah, so if I do 7.1 away from each of these, 52.8 minus 80 or minus 7.1. It's 45.7. And then 81.2 plus 7.1, because that's going another RMS error to the right, is 88.3. And it's even outside of those range for both 40 and 90. So I'm going to say, yes, I am surprised on that one, outside of 3 RMS errors. If it was in between 2 and 3, I'd say I might be surprised, but it's still within 3 RMS errors. When it's outside 3 RMS errors, we're going to say we are predicted, or we are surprised. Okay, you can make a residual plot, kind of like a scatter plot, and what this residual plot is, it shows the distance for each of the dots from the regression line. So this dot right here is above the line, it is this dot, and it's showing you how many standard or RMS errors above the line it is. This dot is below the line, some amount, so it's showing you how far, actually it's not even RMS errors, it's just how many raw data, how much raw data it is below the line. That's what a residual plot is. It just shows how far the error is for each individual dot. Residual plots make it easier to know if the scatter plot is football shaped. So with this one, what we see here is maybe it's football shaped, but also it kind of has this like triangle shape going on. So we can create the residual plot and see if there's the same amount of data below as there is above the line. And that tells you better if it's football shaped or not. This one, I would say, because there's so much data clear up here, I would not use a regression line for this one. I would use something else. You can, but it might not be completely accurate because this is that triangle shape. If you get a residual plot like this, then you know you definitely should not use a regression line. Okay, so this slide is just talking more about the residuals. This shows the residuals. This is what a residual plot should not have a pattern to it. This one kind of does have a pattern to it, but it's not too much of a pattern. There's not enough dots there to really solidify that pattern. So I'm not too concerned about that pattern itself. I think it's okay. The main thing you want to see is it needs to be about the same number of dots above as it is below the line. And there's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And when I said above and below the line, I meant for 0, because that's a 0 error. Okay, the main thing you need to know from that, when we might have scatter diagrams that don't have good residual plots, there's 2 possibilities. If it's football shaped, if the scatter plot itself is football shaped, it's called homoscedastic. If it's not football shaped, if it has more variability to one side, so it's not just not football shaped, but it's specifically more variability to one side. So it has this triangular shape. Variability means like how different it is. As it changes, the error here is pretty small, and then as we go along, the error gets really big. Here is just medium size. It's going out, and that error is increasing. The residual, how far away it is from the line, is increasing as we go to the right. That is called heteroscedastic. Okay, and the way I remember this, scedastic, scedastic kind of sounds like elastic to me. I think elasticity is like how stretchy it is or how far out it goes. So I just think, okay, scedastic, that's like the residuals, that's how far out it goes. And then homo means same, hetero means different. So homoscedastic means it's about the same stretchiness or about the same residual all the way along. Heteroscedastic means it's changing as you go. This one is heteroscedastic. RMS error is only appropriate for homoscedastic. Scatter diagrams. If you don't know what the scatter diagram is football shaped, you should probably do more research before you do your regression line and residuals and RMS error. Okay, chapter 11 homework, we're gonna simplify this down some. So section A, or set A, we're gonna do 1 through 2, and then 4 through 7. B is gone. C was already gone. D, we're going to do just 1 and 2. And for the review, we'll keep 1 through 5A. Okay, this I want done no later than Monday, March 30th. By that time, you should be preparing for the exam plan. I don't know when that will be yet. I don't know if it will be online or in person. We'll just kind of have to play it by ear. But plan on being done with all 12 chapters and be preparing for exam 1 no later than March 30th.